Hello everyone. So let us solve the manufacturing process question. So the first question is flux in welding process acts as. So it is asking about the flux. Like during the welding, if you see, like suppose we have the rod, then the flux can be in the inside or maybe on the outer layer, right? Like this. So when we have electrode, there is another case where we will have the non-melting electrode like the tungsten, but we will put some granules and that will be the flux, right? So what is the purpose of this flux? So the purpose of this flux is to basically first initially react with the metal and it will melt, and after that it will cover the surface so that the oxygen which is top of that will not directly react with the metal. Okay, so it will create a kind of barrier so that it acts in the preservation so that it doesn't get oxide. Okay, so it acts as a protective agent. Okay, not the catalyst, not the filler, not the heat generator, right? In a sound casting, the last liquid to solidify is in the. Okay, so here it wants to say that in a sound casting, like suppose you are doing some casting of something like this, and you have put one riser over here, and you are putting the liquid metal from here. Okay, so this will be somewhat like this. This will be like a sprue, then gate, ingates like this. And when you put the molten metal, so it will fill this cavity, and after that it will rise a bit in the riser. Okay, now so where do you think the liquid metal should solidify at the last? Because now suppose here in this portion we have the liquid one which is solidifying in the last. Okay, this is solidified over here. Okay, and this is solidifying in the last, so there will be some differences, right, because of this contraction of the solidification and expansion of this liquid one, right? So it will create some kind of crack, right? Now suppose we keep the molten metal in the riser, right, enough molten metal. So what will happen during the solidification? There will be some shrinkage, so that shrinkage will be covered by passing some extra metal from this riser. Okay, so that's why the risers which are there, so these are sometimes heated, right, so that the liquid should not solidify over there. Okay, so whenever we have the molten metal in the riser and that is going to solidify in the last, then it gets a good casting. Okay, if another metals like solidifies initially, then what will happen? This may create some gaps, right? Next, X-ray radiography is used to determine them. So X-ray radiography. So radiography, you understand that in radiography we measure the internal defect, right? So here the method is X-ray. We can also use gamma ray. Okay, like this. So radiography, it is used for soundness of the casting. Yes, it is there. Chemical composition, no, we measure through optical emission, right? Then crystal structure, no, this is measured through XRD. Then phases present, it is also measured through this XRD. Okay, next, match the processes given in group 1 with the corresponding typical defects given in group 2. Okay, so in the case of forging, okay, so we get cold shut. Okay. So cold shuts, like in the during the forging, like this basically happens in the die forging. So between the die there is some portion which has got, basically forged such that there it gets some kind of gap over there. Then rolling, we get the alligatoring one. So alligatoring, like we have this plate, right? So this opens somewhere like this, okay, because we have the two rollers. So the outer surface, it is always going to expand more, right, than the middle one. So that's why it creates shape like this. Then deep drawing, so we'll get these wrinkles, okay, and extrusion, we will get these several cracks, okay. Match the joining processes in group 1 with the filler materials in group 2. So in the case of soldering, so it is happening at low temperature, so it will be silver tin, right? Then welding, so welding we can do in the mild steel. Then brazing, then this is done at slightly high temperature, so silver titanium, okay. So it will be like 231. Next, a 200 mm into 200 mm cross section bloom is continuously cast at a casting speed of 0.05 meter per second. The amount of heat extracted from the 0.7 meter long mold is 1.28 megawatt. Assume that the temperature of the steel is at its melting point while entering and leaving the mold. Latent heat of fusion for the steel is 278 kJ per kg and density of steel is 7.8 kg per meter cube. The thickness of the solidified cell emerging from the mold will be, okay. So basically this is a very good question. So what is here, it is given that you have a mold which is rectangular mold, right, and the length of this mold is 0.7 meter, okay. Now when the liquid, it will pass from here, so like here, from here the liquid it is passing, right. So when the liquid it will pass, so basically solidification will start from here, right. So initially it can be like, suppose you draw the cross section, right. So initially some thickness it will get, right. So this thickness it will keep on increasing and ultimately we can get this solidified region, right. This whole region should be solidified like this, okay. So from this mold it is basically getting out, right. So in this case, so when it gets out, so it forms some cell, that means it is not getting completely solidified, okay. So when it is not getting completely solidified, so we will assume that it is emerging with this shell thickness, that is dx, okay. And this is your y direction, this is the flow direction, right. So the velocity of this movement, that is dy by dt, is 0.05 meter per second, okay. Now this there are four walls, right. So this is one wall, this is second wall, and this is third wall and the fourth wall. So heat extraction will take place from all the four walls, right. So when the heat extraction will take place, so this heat which will be extracted, okay, so that heat will be equal to this value 1.28 megawatt. So that means 1.28 into 10 power 6 joule per second the heat is getting liberated, okay. So when the heat which is getting liberated is equal to this much value, right. So now, so when it is getting solidified, right, so the mass of this solidified is getting there, so that is basically releasing this energy. So we can say like the mass flow rate times the density, right, basically the mass flow rate, basically we can say the mass flow rate into times the latent heat, that is giving you that amount of joule, right. So mass flow rate into latent heat is equal to this energy released, energy released. Okay, simply balancing the equation. And since the temperature it is given that it is constant, so if you see like here delta G is equal to delta H minus T delta S. Okay, so we can say here like delta G is equal to delta H, so Tm minus T by Tm. Okay, so the free energy change is basically here we can say it is 0, right? So whatever the energy which is getting released in form of latent heat only. Okay, so mass flow rate, so we'll multiply with density and we'll take the volume. So volume of this cell which is forming, right? So we have the mold, so initially this portion will be inside of this mold, right? So when this portion will be inside of this mold, so we can say like some flow which is happening, means the movement of this mold which is happening. So this portion it has got inside the mold, right? This distance it is nothing but dy, okay, and this distance it is dx, right? So we'll multiply the volume of this region, this dy terms, then this is 0.2 and this is your thickness. Okay, fine. So and this will be in 4 direction, right? So we'll multiply with 4 into this dx into 0.2 into dy by dt, right? So this will give the mass flow rate, okay, into latent heat. So latent heat is how much? It is 278 to 10 power 3 joule per kg. So that is giving us 1.28 into 10 power 6 joule per second. Okay, so now from this we already have the value of dy by dt, so that is 0.05, right? So we will find here dx, so 1.28 into 10 power 6 divided by 278 into 10 power 3 into 7800 into 4 into dx we will need to find, so 0.2 into 0.05. okay, so if we calculate this value, it is 1.28 into 10 power 6 divided by 278 to power 3 into 7800 into 4 into 0.2 0.05. So this is giving us 0.1475 meter. So this value of this dx from here we have got 0.01. So if you calculate the value in mm, so you multiply with 1000, so it will be 14.75 mm. So 14.75 mm. So this will be the correct answer. Okay, so this is how it will be solved. Okay, next. In automobile industry, electrical resistance welding is used for spot welding steel panels, each of 1.5 mm thickness. The weld has an area of this. So area it is 2 into 2 mm square. The current used, that is I is equal to 1000 ampere. The amount of heat required to melt this spot volume is 36 joule, electric resistivity, okay, so rho is also given 8 micro ohm cm. The resistance offered by this spot is, so we know R is equal to rho L by A. So rho it is given 8 micro ohm cm into L. So L, that is the length. So length, when we have the sheets, okay, each of 1.5 mm thickness, the weld has an area of this thing. So thickness, that is, it will be the length over which this conduction it is happening, right? So length will be 1.5 into 2, that is 3, right? So it will be 3 mm divided by area. So area it is 2 into 2 mm square. So mm1 it will be, so it will be 8 micro ohm cm divided by 3 by 4. 1 mm is equal to 10 power minus 1 cm, right? So cm it will cancel. So basically 8 into 3 by 4, so it will be like 6 micro ohm into 10. So we can say 6 into 10 power minus 5 ohm, right? So option B. Now the time required to perform the weld is, now the time required to perform the weld, so here it is given that amount of heat required to melt this is what, so that heat basically will come from I square RT, right? So that is required to melt it. So we get 36 joule. So time we need to find. So 36 divided by IA square. So 1000 into R. R we have got 6 into 10 power minus 5. So we get 36 divided by 1000 to the power 2, right, into 6 into 10 power minus 5. So I got 0.6 second. Okay, so this will be your correct answer. You can check also what is the correct answer. Okay. Okay, so thank you all. Hope this will be helpful for your examinations.